In this video, we're going to look at limits of vector-valued functions. In order to do that, I wanted to review just the concept of a limit first from Calculus 1 and some techniques that might be necessary when you take limits of vector-valued functions here. So here we've got this notation. It says the limit as x approaches a of f of x equals L. That's exactly how we read it. The limit of this function as x approaches this number, so that's this side, is equal to this other value. So in particular, let me give you just an example. Let's say you've got the limit of f of x as x approaches 3 is 5. What we're saying is, as x gets close to 3, from either side, y gets close to 5. So maybe the graph looks like this. As x gets close to 3, the y value gets close to 5. Now it does not bother us at all that when x equals 3, y seems to equal 3. That has absolutely nothing to do with the limit. When we're talking about the limit, we're saying as x gets arbitrarily close to 3, from the left and the right, what happens to the y values? Do the y values get arbitrarily close to something? And if they do get arbitrarily close to a number, what number is that? And in this case, it turns out that that number is 5. So that's that. That's what we mean when we talk about a limit. Now here's just some more notation. If I put a little plus sign up here and to the right of that 3 as a superscript, this means x approaches 3 from the right. Or if we used a little negative sign, that means we're approaching from the left. It's possible for the limit from the left and the limit from the right to both exist, but for those to be two different values. So maybe you've got a function that looks like this. Here at x equals 2, to the left of 2, maybe the limit is 3, so it looks like this. But on the right of 2, maybe the limit is 1. And this isn't to scale, but maybe it looks like this. So the limit as x approaches 2 from the left of this function, I'm just going to label it g of x. We have to take the limit of something, so we're going to put a g of x to the right of that. The limit as x approaches 2 from the left of g of x, that's the y value that this is approaching, as x approaches 2 from the left, that's 3. And the limit as x approaches 2 from the right, as we approach 2 from the right, the y values are approaching 1. So the limit as x approaches 2 in general, remember from Calc 1, if the limit from the right and the left are not the same, we call that a jump discontinuity. And also this is a limit that does not exist. So the limit as x approaches 2 in general of g of x does not exist. This one, the limit as x approaches 3 equals 5, even though the function value and the limit are not the same thing. Now it's also possible that the function value and the limit are the same thing. That means the function is continuous there. Okay, so that's the concept of a limit. A couple more things that you might need to remember from Calculus 1 is how to find limits of continuous functions. So all the functions that you studied before you got to calculus, polynomials, rational functions, exponential functions, logarithmic functions, trig functions, inverse trig functions, multiply those together, divide them, add them together, subtract them. all of those are continuous on their domains. So everything we talked about in the last video with domain, you can't take the even root of a negative number, you can't divide by 0, and you can't take the log of a negative number or 0. All of that still holds. But if you can plug in the particular x value I give you and the y value comes out just fine, and this function's given by a formula, that function's continuous there. So just plugging in the value is enough, and that's going to give you the right thing on the right-hand side. So if you can plug in the number, just go ahead and do it. Also in Calculus 1, we talked about 0 over 0 indeterminate forms. We had a couple of methods for getting rid of these. I'm going to list them here, and then we'll look at a couple of examples. One of them was by factoring and reducing. So you're reducing common factors. So often if we had a rational function, maybe the numerator and denominator both had an x plus 1 in it, which would be a problem when x equals -1. But if we got rid of that, we got rid of those two factors, then the resulting function was continuous. So we might factor and reduce. We also did something called multiplying and dividing by the conjugate. Whoops, divide. I'm changing my verb tense on you, sorry guys. So that's one thing that we did to get rid of 0 over 0 indeterminate forms. And then we also cleared complex fractions. I'd say out of all three of these, the one you're most likely to see in this class is that one. But also remember, as you learned more calculus, after you learned about limits, later you learned about derivatives, and then you learned L'Hopital's rule. If you have a 0 over 0 indeterminate form, L'Hopital's rule is an option for you as well. That says if the limit as x approaches c of some quotient of two functions, gives you a 0 over 0 indeterminate form, or a plus or minus infinity over infinity indeterminate form, you get to do this. You get to say that limit is the same as this limit. So take the derivative of the numerator and denominator and take this limit instead. That's what L'Hopital's rule says. Probably don't use this one as often either, not in this section, but we will be, we might need that a little bit later. This is probably the one that you'll need most in this class, factoring and reducing. And of course we want to remember how logarithms behave and exponential functions behave. So don't forget the end behavior of logs and exponential functions. You should know what those look like. If you don't, that's okay. You're just going to have to review. But here, just in general, natural log of x looks like that. As x goes to infinity, y goes to infinity. As x approaches 0 from the right, y goes to negative infinity. And exponential functions look like that. As x goes to infinity, y goes to infinity. As x approaches negative infinity, so this is a large negative power, the y's approach 0. And if we do transformations of this, we can move this up and down, we can flip it, we can do all kinds of things. The same thing is happening over here. We have so many possibilities, but you need to know what the end behavior is and how it changes under transformation. So keep all of that in mind as we get into the Calc 3 stuff. So now we're going to talk about a limit in Calc 3. Let's say you have r of t, and we're going to say we're in three-dimensional space, but we could just as easily be in the plane or n-dimensional space. All of that would be fine. So r of t is generating a curve c, and maybe our curve looks like this. And at some point there's a hole, who knows, it just keeps going. As t increases, we're tracing out this curve. And R, again, is a pointer. R starts at the origin, and it says you are here at this location with coordinates x of t, y of t, and z of t. It's possible that as t approaches some value a, maybe at t equals a, r of t is undefined, so we have a hole in the graph. Those vectors are getting closer and closer to this limiting vector L. So as t gets close to a, r of t, which is changing on either side, as t gets close to a from either side, all of these vectors, r of t, go from the origin out to here, origin out to here, origin out to here, on either side, origin out to here, origin out to here. As t gets close to a from either side, those vectors approach this vector L. You might say, oh, Miss Townsend, that sounds complicated, and you're right, if I were to draw all the vectors on there, it'd probably make it much worse. But that's the concept. The algebra, the calculus, the calculation part is actually extremely simple. So let's say I want to take the limit as t approaches a of r of t. Well, if we're approaching this point, x is getting close to, well, maybe x of a, or the limit as x approaches a, or as t approaches a of that component. And the y on L is getting close to the limit as t approaches a of y of t. So the limit of this vector valued function is just the vector with these components. You just take the limit of each part. So I may have told you at the end of Calc 2, or maybe even in Calc 1, that if you can do Calc 1, you can do Calc 3. And I believe that that is absolutely true. Maybe the geometric intuition is a little tough for students. But if you can take a limit Calc 1 style, you can take a limit Calc 3 style, because all we're doing is we're doing it 3 times. If we are in 2 dimensions, do it twice. And if you are in 3 dimensions, do it 3 times. If we were in n dimensions, we would do it n times. But you're just taking the limit of all those parts. So as long as you remember your Calc 1 limits, you're going to be good to go. It's really not that hard. The hard part is remembering the old stuff from the very beginning of Calculus 1. So let's look at an example. Let's use that function that we used for our domain example. Let's say we have r of t and it has these components. So in another video, we found the domain of this r of t. And let me see if I can't find what we wrote down there. Our domain turned out to be this sort of really complicated looking interval, or union of intervals. It was -3 to -1, union -1 to 2, union 2 to 9. And any of those x values or t values is a-okay with us, okay? So now let's say we want to take the limit of this function. Let's plug in 0, just to do a simple case. So the limit as t approaches 0 of r of t is this. Take the limit as t approaches 0 of the x component, multiply that by I hat, and then add the limit as t approaches 0 of the y component, multiply that by j hat, and then add the limit as t approaches 0 of the z component. And that's it. That's all you do. You just take the limit of all 3 parts. That's your answer. Say, okay, well, t plus 1 over t plus 1 is going to be 1, no matter what. As long as t is not equal to negative 1, that's a number divided by itself, so it's gone. So this function that remains is continuous at 0. Actually, the original function was continuous at 0. So you can just plug in 0 because that function is continuous there. We're going to get 0 minus 5 over 0 minus 2. So that's 5 halves. This function is continuous at 0. So we get 2 times 0 plus 6. Under that square root, so we get square root of 6. And this function is continuous at 0. So we get natural log of 9 minus 0, which is just natural log of 9. Okay, so that's the limit of this function as t approaches 0. And notice we were able to plug in t equals 0 to all 3 parts. The function's continuous there. It's going to be a nice smooth piece. As t approaches 0, it's just like pointing out to this point. It's pointing to r of 0. The limit as t approaches 0 and r of 0 are the same. So r of 0 is continuous at that point. Okay. So let's pick a point where it's not continuous. Let's try negative 1. So I want to take the limit as t approaches negative 1 of r of t. I'm going to write down my x of t, y of t, and z of t. And let t approach negative 1 for all of them. That's exactly how we take the limit of a vector valued function, sometimes called just a vector function. Alright, now this one's not continuous at negative 1. This one I would get 0 divided by 0. But remember in Calc 1 we said there's a common factor, just factor it out. The limit of the original function is equal to the limit of this new continuous function. So the limit as t approaches negative 1 of this is equal to negative 1 minus 5 over negative 1 minus 2. So the x component we get negative 6 over negative 3, which is positive 2. All right. And then this one is continuous at negative 1, so you can just plug in negative 1. Negative 1 times 2 is negative 2. Negative 2 plus 6 is 4. Square root of 4 is 2. And this one is continuous at negative 1, so you've got natural log of 9 minus negative 1. So that's natural log of 10. Now this function's not continuous at negative 1. Negative 1's not even in the domain. But the x-coordinate is approaching 2. And the y-coordinate is approaching 2. And the z-coordinate is approaching natural log of 10. As we get arbitrarily close to negative 1, r of t gets arbitrarily close to this location, or pointing to this location. So this is our limiting value. Let's look at t equals 2. Same thing. We're letting t approach 2 for all 3 components. If possible. If this limit exists, it's equal to this. Might not be possible. Okay. First, reduce the t plus 1s because t is approaching 2. And we're not even concerned about that. It's just something divided by itself, so it's 1. Notice that the numerator here approaches negative 3. 2 minus 5 is negative 3, and the denominator approaches 0. So this is a non-zero constant over 0, so that's an infinite limit. So it's either going to be plus or minus infinity, and the denominator is going to change signs at 2. So to the right of 2, we've got a negative 3 in the numerator, and let's say 2.1 minus 2 is going to be positive. So we have a negative divided by a tiny positive number. It's going to be negative infinity on the right. As t approaches 2 from the left, say try plugging in 1.99. I get a negative divided by a tiny negative number. That's going to be positive infinity on the right. So x is going to positive infinity when t is less than, just when t is approaching 2 from the left, and x is going to negative infinity when t is approaching 2 from the right. So the limit in general does not exist. And if this limit does not exist, this limit does not exist. So we'll say this is true, which implies that this is true. And if the limit of one of these components does not exist, that means the limit as t approaches 2 of r of t does not exist. So this equality up here is actually incorrect. This is true provided that these limits exist. So when we do this, we're assuming that the limits exist. We assumed that the limits existed here, and we were right. And we assumed that the limits existed here, and we were right. In this case, we said, hey, let's see if the limits exist. Let's assume they exist. And then we were wrong. This one didn't exist. So as soon as we realized that we were wrong, immediately, just about face, this limit does not exist. Therefore, the limit of r of t does not exist. Okay, so we did that one. How about 9? Do you see what would happen at 9? Let's take the limit as t approaches 9, let's say from the left, so that we're in the domain, and see what the limit is. Provided these limits exist, you just take the limit of the x component, the limit of the y component, and the limit of the z component. And if these limits exist, they're equal to each other. All right, these guys are gone. So for the x component, as t approaches 9, the numerator approaches 9 minus 5, the denominator approaches 9 minus 2. So we end up with 4 over 7. Okay, as t approaches 9 here, we've got 18 plus 6. 18 plus 6 is 24. So we have square root of 24. You can simplify that if you want to. You don't have to, though. But look what happens here. As t approaches 9 from the left, so like t is something like 8.99, 8.999, something like that. This is natural log of a tiny positive number. This last limit doesn't exist. So these really aren't equal to each other. I made a mistake. These aren't equal. These are equal provided that the limits exist, and the last one doesn't exist. So let's state that. The limit as t approaches 9 from the left of z of t is the limit as t approaches 9 from the left of natural log of 9 minus t. And here's what this looks like. It has an asymptote, a vertical asymptote when 9 minus t equals 0, because this can't be 0. So we have an asymptote when t equals 9. And this is well defined as long as t is less than 9. If I plug in t equals 10 on the other side, I'd have natural log of -1, which we don't want to do in this class. So it looks like that log graph has been flipped, it's been reflected, and then shifted 9 units to the right. So it's kind of like this. That's just a cartoon. It's not exactly what it looks like, but it's something close to that. This is z of t, y equals z of t versus t. As t approaches 9 from the left, the y values go to negative infinity. So z is going to negative infinity, x is approaching 4 over 7, y is approaching the square root of 24, which can be simplified. But since this guy is approaching negative infinity, that means in general the limit as t approaches 9 from the left of r of t does not exist. And that's it for limits.